The next part of Chapter 6 mostly deals with graphing and finding equations for quadratics. There are three main forms. There's first intercept form. Alpha and beta are the x-intercepts, the zeros, the real zeros of the quadratic. The next is vertex form, the vertex being h, comma k. And the last is standard or general form, ax squared plus bx plus c. The features of a parabola are that they're symmetric. Through the vertex there is always an axis of symmetry. They have zeros, places they cross the x-axis, also called roots. And then there's oftentimes a y-intercept. And these are all key features to a graph. And when you're producing a graph for IB, these are things you should think about including. The vertex is sometimes a minimum, sometimes a maximum, depending on what this value of a is in the quadratic. If a is positive, the parabola looks as it's shown here, opening upwards and a minimum for the vertex. If a is negative, we'd be reflected across the x-axis, and the vertex would be a maximum. So we want to graph two quadratics. First one is written in vertex form. The vertex is the number we're subtracting from x, so 1, comma, the constant being added to the end. So there's the vertex, and we know that there is an axis of symmetry going through it. Because a is negative 1/3 here, we know that the parabola is going to be opening downwards. It's just a question of what's the shape going to be. And to find that, if we had a graphic device with us, a graphing calculator, we could plug in the equation, look at the table, find a bunch of points. But if we don't have one, it's easy enough to pick values for x. For instance, if I plugged in 4, I'm going to get a nice number that after I square it, I can multiply by -1/3 easy. 4 minus 1 is 3, squared is 9, times -1/3 is -3, plus 4 is 1. And because I know that the parabola is going to be symmetric, I can plot both of these points, and I'm able to draw a graph for this quadratic. We could also find the y-intercept point by plugging in x equals 0. It's going to be a fractional value, that's okay. We can also find the x-intercepts by setting y equal to 0, and then we could subtract 4, square root both sides, yada yada yada. And those would probably end up being approximate values. The second quadratic is written in intercept form. Its two x-intercepts are going to be at -3 and -5. And from this we know that the axis of symmetry is going to be at x equals -4. That's also going to be the x-coordinate of the vertex, halfway in between these two zeros. I can find out the y-coordinate by plugging in -4. -4 plus 3 is -1. -4 plus 5 is 1 times 2. The y-coordinate is -2. And we can actually very quickly graph the rest of this. We know that this is based off of the parent function y equals x squared. And there's a very nice pattern for y equals x squared. 0 squared is 0, 1 squared is 1, 2 squared is 4, if we look at the pattern here, we can notice something really nice. The vertical change, if we go over 1, we're going up 1. The next vertical change, we've gone over 1, now we're going up 3. And then the next vertical change after that would be up 5. There's a pattern of odd numbers increasing from point to point. So with our quadratic, because we have a leading coefficient of 2, we're not going to go up 1 first, we're going to go up 2. Then we're not going to go up 3 first, we're going to go up 6. And I can reflect that point to the other side. The y-intercept is going to be up off of this graph paper. There is our graph for the second quadratic. This pattern is something that I found to be useful over the years. If you don't remember it, that's okay. You could have always plugged in values for x and moved forward that way. Now we're going to graph by completing the square. We're going to put this quadratic into vertex form. Remember, to complete the square, we need the leading coefficient to be 1, so I'm going to factor the -2 out. Also, when I was solving by completing the square, we'd move the 3 to the other side, but I want to keep it over here. But I'm going to leave it separate from the rest of the quadratic parts. Now I'm going to fill in the inside, x squared plus, and I'm factoring out the -2. So it's going to be 5/2 x, and then I'll have a mystery number. And we're also going to need a mystery number outside because we have to keep things balanced. So I'm going to take 5/2 and chop it in half. That's 5/4, and then I square it. 25/16 is this mystery number. And I have to keep this equation balanced. I can't just add something without doing it to this other side or doing the opposite of it to the same side. And you got to be careful because we're really multiplying this 25/16 by -2. So what I'm really doing here is subtracting -25/8 from this side. So to balance things out, I have to add on 25/8 to cancel out what I've done here with the quadratic piece. But in doing this, I've been able to factor this into something squared, and that something is going to be x plus 5/4, the thing that I had squared originally. And then at the tail end, common denominator 3 is 24/8, so I have 49/8. The vertex for this quadratic is -5/4, comma 49/8. -5/4 is -1 1/4. 49/8 is 6 1/8. So my vertex is right about there. There's also going to be an axis of symmetry running through that point, and I need some more points to put on this graph. An easy one to plug in would be x equals 0. That's going to get me a y-intercept of 3. So far we have 2 points on this graph, and we know that the axis of symmetry is at -1 1/4, x equals -1 1/4. And when we reflect across that line of symmetry, this second point we found, we do have to be careful because we got to go 1 1/4 away from it, which puts us to 2 1/2. And here we can draw our graph. We could find the intercepts as well. Notice that this does open downwards, and we had -2 for A. But here we found several of the good points we want. We could go further and find the x-intercepts also. Now we want to write an equation. We want to go the other way. And the first equation, the first situation tells me the x-intercepts. So I'm going to use intercept form. And there's actually a better way to write this second factor. We can write that factor in a way that doesn't involve a fraction. 2x plus 1 would give me the same x-intercept. Before we can say we're done with this, before we can say that we have the equation, we need to figure out what A is. And to do that, we're going to use this point that we are given. 3 minus 2 is 1. 2 times 3 is 6 plus 1 is 7. So A is -2. My intercept form equation is y equals -2 times x minus 2 times 2x plus 1. And depending on what the instructions of this said, if it specified a form, I could FOIL this out and expand it to general form, or go beyond that and put it into intercept form. But this is the most straightforward way of writing an equation for that parabola. Now the second one says it touches the x-axis at 3. That can be interpreted two ways. One, that it has a double root at 3, so both factors would be the same, or that the vertex is at 3, 0. I'm going to think of it that way and write down vertex form right there. Again, I need to find A using this point. So I have 25A equals -25. A is -1. And I could expand this out to general form if I wanted to. But with these problems, you have to look at what you're given, what information you have, and from there decide what method is best for coming up with our equation. Here we want the intersection point of two graphs, a parabola and a line. One situation we have is two intersection points, or we could have no intersection points, or we could have the situation where we get exactly one, meaning that the line is tangent to our parabola. But we don't know which it is. Either way, no matter what, to solve something like this, to find the intersection, we want to find out where they have the same ordered pair. I can set them equal to each other. Get it equal to 0. And this one is a prime candidate for completing the square in my eyes. The leading coefficient is 1. The b value, the coefficient of x, is even. So I'm going to use completing the square. So I'm going to bump that 2 over to the other side. My magic number is 4. And now I can square root and then isolate x, remembering the plus or minus. So I have two values of x that work. Now I need to find their corresponding y values. I'm going to substitute into one of the original equations, and personally, I'm going to use a linear one as opposed to the quadratic. Little less work to do. So if I plug x equals 2 plus the square root of 2 in here, we get y equals 7 plus the square root of 2. So one solution point, one intersection point, would be this. The other intersection point I get when I plug in the other 0, x equals 2 minus the square root of 2. So y would be 7 minus the square root of 2. So here are the 2 points of intersection for this line and this parabola. The last problem, we want to know what possible values, what slopes can we have for tangent lines being tangent to y equals x squared minus 4x plus 2, given that the y-intercept is negative 2. So this is a little bit similar to the last problem in that we want to find the intersection point. So x squared minus 4x plus 2 equals mx minus 2. We want to find where they're intersecting. So again, we're going to get it equal to 0. And I'm just combining the like terms. I'm subtracting mx from both sides. So I'm factoring the x out and the negative out. And what I'm looking for here is a quadratic that only has one solution. So I'm looking for a quadratic that has a discriminant equal to 0. So b squared minus 4 times a times c. I want to know, where does that equal 0? So the constant term cancels out. I FOIL the 4 plus m squared out. I get m times m plus 8. So what I get is that the slope of the line either needs to be 0 or the slope of the line needs to be negative 8. I get two values, two different slopes that will give me a line tangent to this quadratic.